Okay, in order to help us determine the basics of power measurement, I quickly soldered up this very simple circuit comprised of a 9-volt battery, a 2K ohm current limiting resistor, a super LED turquoise color, and a 100 ohm resistor that we can use for current viewing or current sensing. Here's the schematic diagram of our simple circuit, and you'll notice that I've annotated the diagram with test points TP1, 2, 3, and 4 in order to give us reference points for voltage measurements that we're going to be taking. What is power measurement? Well, power measurements allow us to determine the power a certain component is either dissipating or supplying to a circuit. And we determine that by measuring the voltage across the component and the current through it. So for example, if we wanted to know how much power this 2K resistor was dissipating, we would measure the voltage across it using TP1 and TP2, and we would also have to determine the current through the component. Then we would multiply those two parameters together, and that would give us power. To determine the circuit current, as I mentioned earlier, I've utilized a 100 ohm resistor here, labeled here as the CSR, and we simply measure the voltage across it using TP3 and TP4. Crunch it through this little equation here. The current is equal to the voltage across the CSR, VCSR, over 100. Please also note that on the diagram I've annotated it with the direction of current flow. In this case, it's clockwise. Conventional current flow is clockwise in this case. So that implies that all four components in this circuit have the same current flowing through them. That's why we can simply measure the voltage across this CSR from TP3 to TP4, put it through our little formula here, and we can get the current that flows around the loop of the circuit. So it does form a loop, and therefore the current is the same through every component in the circuit. Kirchhoff's voltage law states that the sum of the voltages around a closed loop must equal 0. In other words, the voltage drops and the voltage gains in a closed loop must equal 0 when they're all added together. And there is a caveat to this though, and that is that the sum of the voltages will not equal 0 unless the voltages across each component are properly measured. And I would suggest that we properly measure it by starting at the battery and follow the direction of the conventional current flow arrows. So, in this case, I've got my voltage meter leads here, and I'm going to place them across the battery, and that's going to be my starting point. Negative on the negative terminal and red on the positive terminal. Then when I go to measure the voltage across the 2K ohm resistor, I'm just going to rotate and measure this way. Then for the diode, I'm just going to rotate again, and again one more time for the CSR, like so. Sorry, you probably can't see that. There we go. And if we go back to the battery again, we're where we started. Negative on the bottom, positive on the top. So at no time have I arbitrarily decided to flip the leads over or anything like that. I kept them exactly the same orientation as I moved around the circuit. following the direction of the current flow, like so. Okay, let's see if Kirchhoff's voltage law holds. Right now I'm measuring the voltage across the battery. The positive probe is on the positive terminal of the battery and the negative probe is on the negative of the battery. Okay, so I'm going to be writing these values down. 8.42, and now we're going to move the direction of the current flow to the next two test points. And we have a negative 5.43, and move it across the LED. We have negative 2.7, 2.70, and finally across the CSR. And I have negative 0.27. Okay. Now let's see what our trusty old calculator says. So 8.42, 5.43 minus 2.7 minus 0.27 minus, well, 20 millivolt error there somewhere. Probably in my meter, but it's pretty close to zero. Okay, I've redrawn the schematic closer to how I physically built the circuit, and I've annotated the schematic with the voltages that we measured. And just to reiterate, we had the voltage probes across the battery like so, and then I moved to the 2K resistor like so, the diode like so, or the LED, and then the CSR like so. So at no time did I, flip the leads or anything like that. I kept the same probe orientation as I moved the direction of the current flow. So if we start from this corner here and follow the direction of the current flow, we see that we had a 8.42 volt voltage gain, because we went from negative to plus in our voltage. We had a 5.43 volts voltage drop on the 2K. We had a 2.7 volt voltage drop across the LED. And we had a 0.27 volt voltage drop across the CSR resistor of 100 ohms. Now imagine if we had arbitrarily decided to flip the voltage or the probe leads across the CSR, so that we had a plus or a positive probe here and our negative probe here, instead of how we had it like this, because we started out at the battery like this and moved this way. So we would have ended up like that. We would have, if we decided to flip the leads for some reason, we would have ended up with a plus 2.27 volt gain here. So we've now not satisfied our Kirchhoff's voltage law. We know that we would be at least 0.27 volts too high. So that's why, technically speaking, we can't arbitrarily to decide to invert our probe leads across any one of the components in our circuit. We must retain the same probe orientation if we are in fact interested in polarities and satisfying Kirchhoff's voltage law.